Hi, and welcome to 1.3. More on Newton's laws. We've already talked about all the laws. There's nothing really new to talk about in the laws. We're just going to do some more complex type examples. 1.4 is also going to be quite similar. No new laws, just some more complex type examples. So let's start. Example 1. I told you I'd go over this one, I think, in last unit, or maybe even in kinematics. But what is the acceleration of a body in free fall? We all have our hypothesis, mostly because I've told you guys all what it should be. We're scrolling around here. But let's see if we use Newton's laws to prove it. So whenever we are doing a dynamics type question, if you don't know where to start, start with a free body diagram every single time. If object is in free fall by definition means that we're ignoring air resistance and that the only force acting on it is our force due to gravity, which means if we apply Newton's second law, F is equal to ma, our F net statement is only going to contain the force due to gravity, which is equal to mass times acceleration. We also know from our formula sheet that Fg is equal to mg, so we can go ahead and substitute that value in for Fg, and we get that mg is equal to ma. Notice we have mass on both sides of this equation, so we can divide both terms by mass, and on my left-hand side, m divided by m is 1, on my right-hand side, m divided by m is also 1, and we're just left with g is equal to a, which means we get some mathematical proof that if only the force due to gravity is acting on something, then the acceleration due to gravity and the gravitational field strength will always be equal. However, this is where we run into problems, or not problems, this is where it gets more complex. If there's air resistance, and then we don't have the case where G will be equal to A, because you'd have another term in there. Let's take a look at example 2. This one seems a little bit long-winded. Let's draw a little picture, see if it helps us. So a spring is used to accelerate a 70 kilogram mass at 4 meters per second squared along a horizontal surface. So if I'm just going to draw a picture. It's not necessarily going to be a free body diagram. We've got just a mass here. I'll put an M there, and then we're obviously being pulled along a horizontal surface with a spring and to the right, the way I've drawn it. It doesn't give us any directions. So it just says horizontal surface, so you can kind of choose whichever direction makes sense to you. I think most people would choose to the right. During this time, it is noticed that the spring is stretched 0.34 meters. This should say from equilibrium. If the force of friction is 20 newtons, what is the spring constant? Okay, so I'm going to redraw this little diagram, and I'm going to turn it into a free body diagram. So I've got my little mass there. I've just titled it M. I'm going to have my spring force to the right, the way I've drawn my picture. It says there's a force due to friction going left. We always know there's a force due to gravity down, and since it's on a surface, there'll also be a normal force going up. So now, since I have forces both left and right, and up and down, I have two planes. I have both an x-plane and a y-plane, and we never, ever put those two planes together. Even in college level physics, we're not going to do that. They sit in different planes, and we will separate them into planes and deal with them. And then if we have to at the end, we can come to some type of conclusion and put them together. But when we're doing the algebra in between, we never put them in the same plane. We are asked about the spring constant, so I'm going to look at my x-plane. If I get stuck, I might have to look at my y-plane, but I suspect that for this example, I'm just going to look at the forces in my x-plane. I'm going to decide that I'm accelerating to the right because I'm getting pulled by the spring to the right, so that direction is going to be positive. That's my sign convention, which means I've got a positive force from the spring, a negative force from friction, and that's going to be equal to my mass times my acceleration. And what I want to do is I want to keep trying to manipulate this equation until I only have one unknown. Once I have one unknown, then I can rearrange it to solve for that unknown and find it. But there's no real point in investing a lot of time and energy in until I until I know I can find the answer. And right now, I don't know what Fs is. I do know what FF is, I do know what M is, and I do know what A is, so I might as well just commit to this one. I know from my formula sheet that the force of spring is equal to Kx, that's Hooke's law, so I can substitute that value in. Kx minus FF is equal to MA, and then I believe I'm solving for the spring constant. So now I have one expression with one unknown, and the unknown is the thing that I'm looking for. So I'm just going to solve for it. I can add force of friction to both sides. Cancels on my left-hand side. I'm left with Kx is equal to MA plus FF, and my K is going to equal to MA plus FF divided by X. So my K is going to be equal to my mass, which is 70 kilograms, times my acceleration, which is 4, plus my force of friction, which is going to be 20, divided by how far it's stretched from equilibrium, which is 0.34. If we go ahead and plug that into our calculator, I think we will get K is equal to 882.35 to 3 sig figs. K is equal to 882 newtons per meter. Example number 3. I don't know what that M is doing there. It's not getting erased, that's what it's doing. Example 3. A child is sliding along a flat, snow-covered field in a sled. If his initial velocity is 10 meters per second and he comes to a stop over 32 meters, what is the coefficient of friction between the sled and the snow? So, I'm going to do the same thing I've done for every single other question. I'm going to draw a free body diagram. I recommend you pause the video right now and see, even on a piece of scrap paper, if you could draw the free body diagram for this scenario. It's a little bit different than what you would think it would be. So the child is sledding along a flat snow-covered field in a sled. So obviously we're going to have a force due to gravity pointing down and a normal force pointing up. And then I'm going to have to talk about my forces in the x-plane, left and right. So I'm asking myself, does this child have an applied force? You can imagine a child with a velocity going across a snow-covered field. There is actually no applied force. There's a natural tendency to want to put an applied force there, but there isn't. There's just a force of friction that's slowing him down. And notice that our velocity is this direction. So our velocity is to the right. Notice how I did not draw my velocity vector on my free body diagram. It's off to the right. I don't want to get it confused for a force. If it's not a force, it does not go in a free body diagram. Yeah, so those are my only 3 forces. I need to decide now which direction is positive. I've told you guys to guess which direction is going to accelerate and call that direction positive. Since we only have one force and it's to the left, I'm actually going to call to my left positive, and that's going to be my sign convention. So when I look at Newton's second law, sigma F is equal to ma, I've really just got a positive force of friction, and that's equal to my mass times acceleration. Coefficient of friction between the sled and the snow. Force of friction right off our formula sheet is mu Fn is equal to ma, and this is where I'm going to pause and just take a look. I can write that off to the side if you guys like. Ff is equal to mu Fn, and that's what goes into to get to the next line. I'm going to pause and take stock of the things that I have. Coefficient between the sled and the snow, I have in my expression, and I don't know what it is. I currently don't know what my normal force is, so I have 2 unknowns, and I don't know what my acceleration is. So in this formula, I have 3 unknowns. So we're going to have to use some critical thought. We can't just blunder ahead and think about this. It doesn't really matter which one you try and approach first. We have to try and figure out what Fn is. We have to try and figure out what our acceleration is. To find Fn, if we're dealing with a force, if we get stuck in one plane, look at the other plane. So right now I'm stuck in the x-plane. This was the sum of my forces in the x-plane. So I'm going to look at the sum of my forces in the y-plane. And I'm just going to do this down here because I'm going to need some space. So the sum of my forces in my y-plane is equal to ma. I have no acceleration in my y-plane. I am not moving up off the snow or down through the ground. So the whole right-hand side of my equation is going to be equal to 0. In the left-hand side of my equation, I've called up positive, so I'm going to have an Fn minus Fg. And on my right-hand side of the equation, that's still equal to 0. If I add Fg to both sides, I get an Fn is equal to Fg. I can then substitute this in for Fn. Mu Fg is equal to ma. And I'm just going to go ahead and simplify that Fg into mg because we know that Fg is equal to mg is equal to ma. And many people, when starting this problem, would have been upset because I didn't give them a mass. They'd be like, oh, I can't solve this problem. I don't have a mass. And if your initial inclination is to shove numbers in right away, you'll get stuck there and you'll never really move forward. But if your inclination is to use some critical thought and to look at some things, and I'm just moving this down because we're going to need some more space, and try the algebra before we substitute numbers in, we end up being able to divide both sides by mass. This is independent of mass. It doesn't matter how large the child is. Mu g is equal to a. I still don't know what my acceleration is. But I do notice that in the question, they give us enough kinematics details that I can find the acceleration using kinematics. I have an initial velocity, which is 10 meters per second, and I've decided that to the left is positive, so my velocity is going to be negative, because it's to the right, negative 10 meters per second. And my displacement is also going to be negative 32 meters because I'm also displaced to the right. He comes to a stop, so my final velocity is 0, and I'm trying to find my acceleration. I think for this one I can use a Vf squared is equal to V naught squared plus 2AD, and I'm going to maybe actually see if I can take this whole thing and move it somewhere that's going to be less cramped. Let's take that, move it over here. Yeah, that looks better. I don't know what happened to that V and why it got left behind, but we can try and move it too. Yeah. So 0 is equal to V naught squared plus 2AD, since my final velocity is 0. If I algebraically rearrange this, I get a negative V naught squared divided by 2A is equal to D. And if I go ahead and substitute my numbers in, I get a D is equal to negative, a negative, my ratio's not working, negative 10 squared divided by, oh, I made a mistake there. That's supposed to be, I'm solving for A, which means that's a D, and that's an A. Third try is lucky. A, divided by 2 times negative 35. And I get that my acceleration, which I've written down up here, let's see if I can pull it down. My acceleration is going to be 1.56. Oh, I lost a 1. So now I have my acceleration. I have my g. I know everything in this expression except for, oh no. I don't know why my tablet seems to be glitching out today, but today's the day. I can now solve for mu. Mu is equal to A over G. Again, if I plug my numbers in, mu is equal to 1.5625 divided by 9.8. I get 0.159. take that, put it in there. So to 3 sig figs, 0.159. Mu should be unitless. So I'm done. Notice how I kept all of my decimals for my acceleration because it was not a final answer, and then rounded back to 3 sig figs once I was at a final answer. Example number 4, and I believe our final example for this video. A 5-kilogram book is held against the wall with a horizontal applied force. As the force is reduced, the book starts to slide when the applied force is 456 newtons. What is the coefficient of friction between the wall and the book? So you could do this at home. You can grab a book, you can use your hand, you can push it against the wall, and then slowly reduce the force on the book until it starts to slide. And that's essentially what you've done here. So I might draw the wall on this one, just because it's a little bit more complicated. And then I'm going to draw my book as just a dot. So what I'm doing is I'm applying a force on the book into the wall. The wall, of course, is going to push back on the book. Fn. And we know that Fg will be pulling down, as always. So the question is, what is keeping the book where it is? Well, it must be a force of friction counteracting the force of gravity. Notice how, again, I have forces in both planes. I have forces in both my x-plane and my y-plane. And I might have to look at both of those planes. It asks about my coefficient of friction, so I might as well start in my y-plane. The sum of all my forces in my y-plane is equal to ma. We're looking at right before the book starts to move. So there is no acceleration. It's still being stuck there, so my acceleration will be 0, which means I'm left with the sum of my forces in my y-plane will be equal to 0. I've got no motion, so I'm just going to call up and write positive, because that seems like the easiest default thing to do, which means the sum of my forces in my y-plane are going to be a force of friction minus the force due to gravity is equal to 0. I can add the force due to gravity to both sides, and I get the force of friction is equal to Fg. I have things from my formula sheet that I can substitute into this. I know that my force of friction is equal to mu Fn, and I know that my force due to gravity is equal to mg, so I can substitute both of those things in. I get a mu Fn is equal to mg. Now, what some people are going to do, and it's going to be wrong, is they're going to assume that Fn is always Fg, even though I've said many, many, many times that the normal force is only the same as the force due to gravity if you're standing on a horizontal surface and not accelerating. We are not standing on a horizontal surface. So in this case, Fg will not be equal to Fn. The normal force is not equal to the force due to gravity. They're not even in the same plane. So what we're going to have to do is we're going to have to look at the x-plane. I might actually move this back up there because I think I might have enough space to do what I need to do there. So I'm going to look at the sum of my forces in my x-plane is equal to ma. When I'm looking at, again, I'm not accelerating left or right. I'm not crumpling into the wall or bouncing off the wall, so my acceleration is going to be 0. I've called right positive, so Fa is positive minus Fn, and that's going to be equal to 0. So I find that in this case, Fa is equal to Fn. So I can go ahead and substitute that back in to my y expression, and I get mu Fa is equal to mg, and I can solve for mu because I'm trying to find my coefficient of friction, mg divided by Fa. Again, if you love throwing numbers in right away, you're really going to struggle with this now. We've been trying to practice doing algebra right from the very beginning of this course without the numbers, and now it's really becomes much more impossible to do putting numbers in right away. I think if I put numbers into this, mu is equal to 5 times 9.8 divided by the applied force, which is 456. I believe this might be my answer up here. And I can take that guy down. And mu is equal to 0.107 or to 3 sig figs. Mu is equal to 0.107. Again, mu is unitless, so we don't have to worry about units. And that is our final answer.
Thank you for watching, and I just wanted to remind you guys a couple of keys for success. Number one, you got to do the practice questions. If the things I'm saying make sense, that's phenomenal, but you still have to practice and make some mistakes on your own. And that goes along with number two. If you get stuck, ask me questions, get in touch, write me an email, make an appointment, or leave a comment on the YouTube video. And step number three to success is look after yourself. Eat good food, get some exercise every day, and socialize as much as you can right now. I hope you guys are all doing well, and I will talk to you soon.